Okay, for the third lecture for Chapter 7, we're going to round it out here with niche shift. Even species that have a gradual morphological change, individuals may have different ecological roles depending on the size and age. And so, again, this is focused on the life cycle. So, um, occupying a different ecological niche depending on your stage in development, effectively. And we look at ecological niche, which is the physical and biological conditions that the organism needs to grow, survive, and reproduce. So in the in the stream insect example, larval stage, freshwater stream bug, adult stage, winged insect, different ecological niches. And there should be an optimal time to undergo metamorphosis or any niche shift that maximizes survival. Niche shifts should occur when the organism reaches the size at which conditions are favorable in the adult habitat, more favorable in the adult habitat than the larval habitat. Meaning that, again, probably an extreme example of this are individuals that have a larval stage that's caterpillar-esque, apple maggot type things that really only hatch to mate and disperse. And so, they're timing their movement related to that. Or in the example of frogs and tadpoles, at a certain point, if you're a large tadpole, there could be a disadvantage. Maybe you're more likely to get preyed upon. In the salmon world, an example of this is Pacific salmon, particularly coho and chinook, can live in streams for either a summer, a year, or even 2 years. And so they're changing their niche from stream to ocean depending on what those conditions look like. If stream conditions are more favorable, maybe there's a higher percentage that stay in the stream for a year or 2 years. If stream conditions are not favorable, then they might make that choice to move out into the ocean where there's more food resources, but also increased risks of predation. And so the Nassau grouper, small juvenile fish hide in algal clumps and larger ones stay in rocky habitats. And they found that this has to do with the smaller juveniles are very vulnerable to predators in the rocky habitats, but larger ones are not. Pretty common idea of a nursery habitat. Locally, another example of that that's often cited is eelgrass, and we talked about eelgrass earlier. It's a marine angiosperm, and they form these large eelgrass meadows, the largest one on the west coast being just south of us at Padilla Bay, or Padilla Bay, depending on how you pronounce it. And that's a massive habitat for juvenile Dungeness crabs, salmonids, things like that, where there's a three-dimensional structure that they can hide within. So for here, small Nassau groupers are hiding in algal clumps, and larger ones are able to cruise around these rocky habitats. Three-dimensional structure provides nooks and crannies for places to hide, and while that, in this case, algal clump, or in the eelgrass example, maybe the prey within that are also relatively small sized, and so as you get bigger, you need bigger food, so you need to move to a new location to maximize growth, and you want to time that with, am I big enough that I'm not going to get hammered as soon as I leave the safety haven of this protected habitat? And if larval habitat is favorable, metamorphosis may be delayed or eliminated. Some salamanders mature sexually while retaining larval morphology. Pedomorphic So they kind of skip the moving to the adult phase and retain their larval morphology. Mole salamanders have both aquatic and pedomorphic adults and terrestrial metamorphic adults in the same population. Frequency of the pedomorphosis in these mixed populations depends on factors such as predation, food availability, and competition, which influence survival and growth in the aquatic habitat. So here is the pedomorphic version and then the terrestrial metamorphic adult. You can see the changing gills here, tail size, so one that's obviously adapted for the aquatic environment and one that's adapted for the terrestrial environment. It's pretty interesting where they can just kind of skip, basically if the water's good, like don't leave it. If the water's not performing an ideal habitat, now they have the option to move to the terrestrial habitat, undergo metamorphosis, and then get engaged in sexual reproduction. Or here they can maintain the larval form and still undergo sexual reproduction. So it's a pretty interesting example of plasticity. So depending on what's happening in the environment, organisms are able to capitalize on those changes. This is a good one. So the number of reproductive events during an organism's lifetime, the two big terms we use are simiparous and idioparous. Simiparous, they use the annual plants as an example, which is true, and like the agave thing is pretty crazy. We got a picture of that next. The agave thing is pretty interesting to be an organism that lives to be 40 years and you only reproduce once. Locally, the giant Pacific octopus is a great example. I think most people immediately jump to Pacific salmon. Many of them are simiparous. There are, depending on how one defines Pacific salmon, if you include steelhead, then they can be idioparous, but generally we don't. We can get into the semantics of that later, but Chinook, chum, coho, pink, sockeye, spawn and die. The giant Pacific octopus is an interesting example where they take their last, ounce of energy and protect the eggs. A total aside, but if you haven't seen My Octopus Teacher on Netflix, it's well worth watching. It's a pretty cool documentary of this guy who goes skin diving every day with the octopus in South Africa. It's really similar habitat to here. I mean, it's a bit warmer. He's not wearing a wetsuit the whole time, but and you get idioparous species that can reproduce multiple times, most animals, many kinds of plants. So different life history strategies. What did I have to say about simiparous that was interesting? Yeah, there was this bivalve clam I studied in grad school called a donax, called a bean clam. They're really tiny. I don't think they're fully, I wouldn't classify them as simiparous, but they were interesting in that they didn't seem to live more than a year. So you would have these clams that grow fast and spawn, and they probably spawn, over a period of months. But then in the winter, the population would die out, and then next year, new recruits would show up, and so it was really fascinating little guy. We never totally worked that out, but presumably they don't really live more than a year. We'd get some overlapping age classes, but not really much. It was kind of crazy. And then here's that example from the book of an agave. Sometimes called a century plant, I believe. And so, luckily for the agave, they also undergo asexual reproduction. And so, you'll have an individual that might take till 40 years for it to grow the stalk and produce sexually, but in that time, they're also budding and forming clones. Interesting thing about these is, flowers don't look very white, but in most desert plants, rely pretty heavily on moths and bats for, I was going to say fertilization. What's it called in plants? Pollination. There we go. Clearly a botanist. They often rely on bats and moths for pollination. So you see a lot of white flowers in the desert. Sometimes the flowers only open in the evening to facilitate that. And we'll get into like deeper detail about R and K, but no ecology class is allowed to exist without a discussion of R and K selection. R is selection for high population growth rates, an advantage in newly disturbed habitats, uncrowded areas. And R is the intrinsic rate of increase of population. We'll talk about K, which is closer to carrying capacity, more stable. A few different ways of kind of memorizing these. R, rapid, rapid growth. R like rabbits, lots of young. Where K is near carrying capacity, obviously C and K, but yeah, it's kind of the same noise, right? So K closer to carrying capacity. I'm trying to get what's a good animal to K that reproduces slowly. I was thinking camel. That's obviously a C as well, but fewer young, longer time for the populations to grow. So K selection is lower growth rates in the populations that are near K, which is the constant used for carrying capacity in populations equations. This has an advantage in crowded conditions where efficient reproduction is favored. So the idea being that if two species land in an open habitat where neither of them have competitors, they land in a field with no other herbivores and they're both herbivores, the R selected species is going to reproduce like crazy and take over. And the K selected species is going to grow slowly, have a few offspring. And so in a newly disturbed area, the R species will take over. Over many generations, the K species may be able to establish some dominance through maximizing those stable conditions. So maybe having larger young, care for those young more to be able to get through deep dips in productivity over time. I'm losing my voice here. So R selected species live fast and die young, short lifespans, rapid development, early maturation, low parental investment, high reproductive rates, insects, small vertebrates like mice, and weedy plant species. Make lots of young, don't send them to college, and just keep going because you're going to die pretty soon. K selected species are slow and steady. These are long-lived, develop slowly, they have a later maturation, they invest heavily in each offspring with low reproductive rates. Large mammals, reptiles, long-lived plants. You could think of elephants as an example, orca whales as an example. Things that live on the order of 80 years and have one offspring every 2 to 3 years. Most life histories are intermediate between both extremes. And there's a comparison looking at 3 Australian butterfly species. One in drier, less predictable habitats had the more R selected, and 2 species found in more predictable forest habitats had the K characteristics. So in the stable habitats, being K selective might make more sense, where you're able to invest that time and energy into fewer young, more care for each young, and then there's less, there's higher survivorship for those few individuals. And then we'll look at this classification scheme for plant life histories based on stress and disturbance. Stress is any abiotic factor that limits growth, and disturbance is a process that destroys plant biomass. Mudslides, fires, stress would be a drought. I'm trying to think of another disturbance that would be good. That's like a natural disturbance. Flooding, did I mention flooding? I don't know. Fire, yeah, mudslides, flooding, things like that. So in low stress, low disturbance habitats, competitive plants with the superior ability to acquire light, minerals, water, and space have an advantage. You could think of low stress, low disturbance, competitive plants with superior advantage, things that can grow taller and throw out a larger canopy, old growth trees, things like that that take a long time to outcompete. So if we look at the succession of a forest, it'll start with maybe something more like these rudderalls, which I'll get to in a second, but it might start with the more weedy species, then maybe Doug firs, and then the cedars grow up in the shade and ultimately outcompete the Doug firs by growing taller and throwing out a bigger canopy. And then they wind up being the dominant major plant species in the area. But that whole process takes 500 years. So you have to have a relatively low stress, low disturbance habitat. In an area with relatively low stress, meaning everything's good, just every few years the whole place gets wiped out, high disturbance habitat. Plants with a short lifespan and rapid growth rates, such as rudderalls, are favored. They can exploit habitats after disturbance has removed competitors. Maybe an area that floods every couple of years and wipes everything out. We'll continually have these rurals come in, short, weedy, punchy little guys that come in, take over, do well, kind of crowd out the system, and then get wiped all out again. And in high stress, low disturbance, you've got stress tolerant plants that may have a slow growth rates, evergreen foliage, low water and nutrient use, and a low palatability to herbivores, and the ability to respond to favorable environment, temporally favorable environments. What that means is, I'm thinking of high mountain, sort of like alpine trees that might have a growing season of 2 months, right? So when lights out, they're able to make enough energy, can store enough water, and they can make it through these areas, but they're not likely going to be disturbed, which is why we can have these high mountain pines that are on the order of 2,000 years old. If you can live for 2,000 years, you are in a low disturbance area. But it's very stressful. You're frozen 9 months out of the year and you get 2 months of growing season. Not ideal. So you're a pretty stress tolerant plant. And so we can think of this stress tolerant, competitive, and rudderall. So here they're having stress tolerant, meaning cacti, sure. Many cacti can live for as well a long time. It's not a creosote bush. Man, I can like picture it. I'm blanking on the name. It's not saguaro. Shoot. There's a southwest plant I'm thinking of that has like long. Anyway. Man, it's gonna bug me. Many of these species live for hundreds of years, and they're able to tolerate a fair amount of stress. Competitive. I'm gonna grow bigger and outcompete you. Rudderall. The whole place just got nuked and I'm going to take over. So we can think of it kind of in this triangle of competition, disturbance, and stress. And I believe it's Charnov. This is kind of a funny one. There's this Charnov's, and it doesn't really have a principle, but like this Charnov continuum or this Charnov index is a proposed scheme that removes the influence of size and time. So age and maturity are positively correlated with lifespan in many species. So to remove the effective lifespan, we divide the species' average age of maturity by its average lifespan to get a dimensionless C ratio. So what this is saying is, if we want to compare if we want to be able to directly compare how long it takes an elephant to mature compared to how long it takes a beetle to mature, well, the beetle could be weeks, but they might only live for months. And an elephant, it was like 15 years, but they live to be 80. So clearly the elephant's more. Well, we need to normalize that data, the data of maturation. We need to normalize that by the expected lifespan of the individual to get an idea of like what ratio of your life does it take for you to become mature. So this is the dimensionless ratio because we're dividing years by year, so the years cancel out and we just get the C value, which differs between ectothermic and endothermic animals. It's sort of interesting. It takes fish and lizards longer to mature than mammals and birds using a C ratio, which is kind of a trip, and we'll walk through it a bit here. So for birds, that ratio is 0.37. So if you live to be 5 years old, you would mature well ahead of that at a little over a year, under 2 years, which is true for a lot of fish. And think birds. I'm thinking of, what am I thinking of? Chickens, maybe? Yeah. I mean, a fair number of birds kind of live in that 5 to 10 year range and really become mature after year 1. Mammals, 0.77. So if the average lifespan of an adult would be 5, their average age of maturity would be just under 4. That's actually pretty long. And we'll get into where this starts to break down. Okay, well now, what if our C value is greater than 1? What if our C value is 2.2? Okay, so the average lifespan of an adult is 3.4 years, and the average age of maturity is 7.2. Well, that's a problem. You're going to die before you get sexually mature. If that's true, how come we have fish? How come they're not all dead now? If they only live for 3 years and it takes them 7 years to get mature, they should all be dead. And so another way you could think about this is it's also directly related to number of offspring and survivorship of those offspring. One of my fisheries professors said, on average, fish shouldn't exist. Or on average, fish don't exist. Which is partially true here. Meaning that, if you're a broadcast spawner and you have 100,000 eggs, only 2 of those need to survive to keep the population stable. So that means almost 100,000 of them are going to die. So on average, you're not going to make it by a lot. And so that's one way we could look at these numbers that are below 1. A 1-to-1 ratio would be you mature at the age that you become an adult. So this is kind of a compounding factor here. Could be, predicted average lifespan. And so Charnoff's scheme may be most useful when it comes to comparing life history strategies across a range of taxonomy or size. Grimes is mostly used for plant taxa, kind of weedy versus etc. And the RK continuum is useful in relating life histories given population characteristics. Okay, I'm going to stop there. The next piece goes back into some of the reasons why fish might have sequential hermaphrodism, including the book does go into detail about California sheephead, which is kind of the opposite of what what Nemo does. Okay, and that should wrap up chapter 7.